Hello, everyone. My name is Patricia Rodrigues. I'm going to talk today about the fundamentals of iMineralysis. And I call it a revolutionary way of doing multimedia analysis by improving acceleration and accuracy using artificial intelligence. Before I start, I want to give a quick multimedia analysis summary. That's not intended to talk too much about multimedia analysis, but I want you to know about that multimedia analysis is an inversion process to estimate simultaneously the volume of minerals and fluids in the reservoir from well logs while honoring the input log data. This technique has been around since the 1980s, and so it's very well known, very well documented. And many commercial software provides a module to do this kind of analysis. We have in PowerLog, it's called Statmin, in Lisa, it's called Minerva, in Geolog, it's called Multimin. We have in Decision Space, we have in IP, it's called the Mineral Solver, and in TechLog, it's called ELAN. This is a powerful tool, especially in complex lithologies, but it's rarely used, and it's often misused due to the difficulty of finding appropriate matrix coefficients for the problem. I've been teaching a multimedia analysis, a very generic class, since mid-2020, and we have had around 120 students in that class so far. And our experience has been that even though they are interested in doing the multimedia analysis, it's not that used, and we are hoping that with our iMineralysis tool, people get more access to it. So the focus of the iMineralysis tool is in that difficulty of finding the appropriate matrix of coefficients. What I mean by the matrix of coefficients is this table of constants that tells you the properties of the minerals that you want to solve for. So in the multimedia analysis, you get the input data, which are your logs, whatever logs you have available, and you are solving for the volume of the minerals. So, but in able to do that, you have to give it the corresponding properties of each of your minerals or components, also like the gas and the water or oil. So we are focusing the iMineralysis tool in helping us solve for those matrix of constants. So in summary, iMineralysis, and I'm going to give a summary of iMineralysis now, and then I'm going to explain you how we do it. It introduces a genetic algorithm to search for the matrix coefficients. It allows the estimation of those mineral coefficients in areas where the coefficients are uncertain. It automates the time-consuming manual trial and error process of estimating the mineral constants. And because of all that, it allows the petrophysicists to explore spatial variations in important parameters such as water resistivity, kerogen maturity, and clay composition. So the typical process of like regular multimedia analysis in any commercial software follows this kind of schematic representation. So it starts with generating a matrix of coefficients, so like the one that I showed in the previous slide. The software then goes and solves the linear system of equations. It provides you with the volume of minerals. It then also provides you with the estimated logs. And then the user inspects basically the misfit between the model logs and the real logs. If we consider that acceptable, we're good. We export or use the data for the next steps. If not, we have to do a manual adjustment of the matrix. So, and this is the difficult part for any petrophysicist or geologist or geoscientist in general. So we decided to add some automation via the artificial intelligence for all these steps. So the original, like the initial generation of the matrix coefficients, and also how we evaluate the results and how we adjust the matrix. So artificial intelligence is a computer system that is able to perform tasks that ordinarily require human intelligence. The idea of it is to replace or automate a process or part of a process. So we still have to have good quality of the input data, and of course we get still the same kind of outputs, but we're here focusing on the process. So what is the genetic algorithm? It's a global search heuristic algorithm based on natural selection and recombination. It iterates over groups of generations of possible solutions that we call individuals, starting from randomized initial generation. Each individual in a generation are ranked, and the best individuals are randomly paired and combined to form a new generation. Then the iterations continue for a certain number of generations or until a good enough individual is found. Genetic algorithms are good optimization option when the problem can be decomposed into building blocks, basically subparts of a larger optimization problem, which is the case of the multimedia analysis. So how do we use the genetic algorithm in our iMineralysis tool to solve the multimedia analysis problem? First of all, what is an individual? Well, in our case, an individual is a single matrix of values. In the genetic algorithm, we translate that into a string, but that's just an internal way to use the genetic algorithm. How do we rank the individuals? Well, we compare the measure versus the model logs, and that's done in the entire interval. The multimedia analysis is solved one depth at a time, but we compute that error between what we model and what we input as the raw data, and we add that error in the entire interval, and then we can rank the quality of each of the matrices that we are evaluating. Then, after we have ranked and we have selected the best individuals, how do we combine them? It's called crossover. Well, the crossover is basically taking two of the best individuals and just mix the vector in different ways, and there are different rules to do that. We also add randomization and mutation to ensure that good values are available for selection. And what I mean by that is that we're taking, for example, you have 20 individuals in one generation. We're selecting the first 10 or whatever number the genetic algorithm selects as the best. We combine those, we keep the best of them, but we also add another random ones, and we also take like the best and we do a quick mutation of that. So how does the workflow changes based on the new genetic algorithm? So we introduce the genetic algorithm allows us to generate n random matrices of coefficients given the ranges that we give to it. And so we, instead of evaluating one set of coefficients at a time, we have an n number of them. We then apply the linear system. Basically, the multimedia analysis kicks in and makes the solution, the multimedia analysis solution for each of the matrices. So you get n numbers of solutions, and you can then also have the calculation of the model logs. And with that information, then we can rank. So we can evaluate each of our matrices based on how good the fitness was. So with that computation of the misfit for all the depths from the logs model using each matrix, we make decisions. If we're in the final iteration, it doesn't keep looking. If it's not there, then it takes the best solution. It does that adaptive adjustment of matrices using the genetic algorithm. And we keep going until we're done with the iterations. And now we don't have to adjust the matrix of constants. We just basically adjust the limits. So what do I mean by the limits? And as I mentioned, in the multimedia analysis, we're solving this linear system of equations. And that's the input to our software. We have to add one constant for each of the logs. But in the case of the iMineralysis software, instead of adding a constant, we're actually using a range of, we use the range of the property. If the range is well known, then that range is very thin. It's not, you can get a wide range of numbers here. So the genetic algorithm then allows us it can yield almost perfect log prediction. So the plausible solution is not necessarily the best until it's calibrated, but it gives you very good results. So the inputs to the software is a table of constants that instead of having one number for each of the combination of logs with mineral, you get actually three. You get the minimum, the coefficient, and the maximum. And you start with an initial matrix, and then you get, after you have run the program and obtained the volumes, you also get a final matrix of coefficients. So you get the volume, the constant value that gave you the best solution as an output as well. So you get, for the standard forward modeling, you get two outputs. You get the volume of fraction of minerals and fluids, and you get the model logs. And for the iMineralysis optimization, you actually get 3 different outputs. You get the volume of fraction of minerals and fluids, you get the model logs, and you get the constituent properties. So the potential application of iMineralysis beyond acceleration. So one of the things that is a clear advantage of iMineralysis is the acceleration of the inversion, the multimedia analysis inversion. But in addition to that, because of this quick way of solving the multimedia analysis, you can also identify kerogen grain density trends versus thermal maturity, for example. You can also independently quantify variable water resistivity trends. You can analyze large number of wells with expected regional variations in mineral properties. And all that because you can solve the multimedia analysis in each of the wells independently, and that will provide you with the properties of the constituents in each well. And one example of that is this example from the Marcellus shale. We have a cross-section in which we have a big change in depth. The Marcellus shale is an organic rich interval. And we have here to the right the multimedia analysis solution that we did independently in each of the wells. And we can see at the top that we have the vitrinite reflectance going to very low maturity wells to over mature kerogen. So for each of the iMineralysis solutions, we evaluate how the density of the kerogen changes from the initial number that we gave it to the optimized value. And we focus on the optimized, or basically the changes that occur in the kerogen density. We then plotted the kerogen density versus the vitrinite reflectance, and we can see a very nice correlation. And it's what we expect. We're expecting that the density of the kerogen increases with maturity. So we have higher maturity and increase in the kerogen density. And we can see that, as expected, the vitrinite reflectance increased with depth. The good thing about this is that we can then plot or interpret regional variations of these properties. We have an example here in a different project. This is not the Marcellus project, in which we plotted the kerogen density in a large area. So the higher colors indicate, in this case, higher kerogen density. And this kind of map they're really unique to iMineralysis. I mean, in any other software, it's practically impossible. It's theoretically possible, but it's practically impossible to do this kind of map. You cannot optimize the kerogen, the matrix coefficients for each of the wells individually and then create this kind of maps. You can see in this example that we had an increase of kerogen towards the center of the basin and indicating a higher maturity, and which was actually correlated to the temperature in the area. We see that in this same case, a decrease in water conductivity towards the south. And if we had independent data like the temperature, we could correlate that or not with changes in salinity. So iMineralysis introduces a genetic algorithm to search for these matrix coefficients. This is the same summary that we showed at the beginning. It allows the estimation of the mineral coefficients in areas where the coefficients are uncertain. It automates the time-consuming manual trial and error process of estimating mineral constants. It allows also the petrophysicists to explore spatial variations in important parameters such as water resistivity, kerogen maturity, and clay composition. Okay, now we're going to start showing you a demo of the iMineralysis software. This already has the project open, and I'm not going to show how we load LAS data or how we set up the logs or where we select samples. We have all that capability here. We're going to jump to the setup analysis, in which we do the multimedia analysis part of the software. So in this part, the way I'm going to run the demo is that I'm going to run the software twice. The first time I'm going to run it like any typical multimedia analysis software. And then I'm going to run it again using the optimization features of iMineralysis. We left we call it the forward modeling option, which is the equivalent to what Elan or any other software does, just in order to show you the comparison. One of the differences that we have in iMineralysis is that besides having the coefficients for each, like the properties of each of the constants, we also have what we call the ranges. So we have the minimum and the maximum. So for each of your minerals and each of your logs, you not only enter one number, you actually enter the range. It is also possible to run the multimedia analysis without even entering the middle point or like the coefficient, the initial coefficient. You can actually just use the minimum and maximum and set up your ranges. So after you have done that and click apply, we go to analyze. In prepare analysis, we select the search limits. If we want to use that initial coefficient, we can also select that. And as I said, I'm going to run it with the forward model option instead of the optimize, just for your comparison. And we select the name of the results and we click on prepare. And I want you to take a look, because in the we're going to do also an example with multiwells, and we're going to talk a little bit more about this screen. This is just a kind of a diagnostic screen to make sure that before you run the model, everything is in order. So we click on start, and it takes you directly to the results window. You have your logs. This is your model logs versus your input data. You can see that the solution is very good. We can then, in a typical multimedia analysis, and I didn't show the calibration data, but for this well, what we're expecting is a volume of kerogen between 1% and 5%. We are expecting 20 to 30% of quartz, and we see that even though the solution seems reasonable based on the model logs, still the fit is not perfect, and also it's not really giving us the calibration that we expected. And we can see here the kerogen is approximately 10%. It's much more than we expect. So the way a typical multimedia analysis workflow will go is that you go to your table of constants and you change some of the constants that you input. And I'm going to change that. I'm going to change also, for example, the conductivity of the water. That's kind of a trial and error process. Of course, those changes are always done with certain criteria. It's not done randomly. And you go to analyze again, go to prepare analysis. I'm just going to call it now version 2. And we run the model again. Okay. And you get your new results. You can, in iMineralysis, it allows you to easily compare between two different models that you just ran. So you compare the initial model versus the new model. And you can see in the new model, the version 2, we have now more oil in the system. This is actually this well just produces oil. You have now less kerogen. And this is what a typical workflow will look like. You will go ahead and go back and change your constant. But in this case, instead of doing that, what we'll do is that we're going to use the optimization. So optimization will run 100 generations with 20 individuals. This is actually 2,000. It's going to test 2,000 variations of the constants. And the variations, as I said, is going to be between the limits that we had set up. So I'm going to call that run the optimization option. So we click in prepare. I'm going to say yes. We click start. And now you see a different window. Now it's showing you the results of the optimization. In each of this, and I want to focus only that blue line because we don't have time to go into all the details. But you can see in the blue line that the fitness of the model is improving with time. So you have in each generation is testing and is finding a matrix of coefficients within the limits that we gave it that is best. Usually, typically for the middle of the range, of the middle, like at 1,000 test, is getting to a very good solution. We also have in this screen here, we can see the numbers that is testing. So within the range of gamma ray, for example, for the kerogen, it started in this green line here. This is the original, the initial value. And the red bar tells you the range of value that is testing in each generation. And it's always keeping, in this case, that blue line at the top. For other numbers like the water, you can see that it changes more quickly. And now for the optimization, this is the blue solution here. The left, always the last results are found on the left. And this is the compare. We can compare that. We can change the comparison to the more recent one, the one that we just did some trials and improved the results. We can see now that we have much more quartz, we have much more oil, we have less kerogen, which is really what we expected in this well. We can, if we zoom in, we can zoom in and see how the blue solution is now on top of the red. You can hardly see that red. You have to go and hover on top of the logs here to put that curve on the top. So you can see here the red. This is the input data. This was the green is the our latest estimation before we did the optimization, and the optimization is in blue. So we have now almost a perfect match of the model logs with the raw data, but also we got a much better geologic solution. We also get in this tab here in the coefficients, the final optimization metrics. So we have your starting coefficients that were in the middle, and the ones that will be the equivalent of if you run it with TechLog. But now you have the final optimized number. So for example, for the density of the calcite, starting 271, now it's 271.74, which it makes sense because in this case, the calcite is really representing a mix of carbonates. It has mainly calcite, but it has some dolomite as well. So it made it, it may be possible that this is larger than that. Okay, so I'm going to switch now to another example in which we run this for several wells, so you can see the difference. Okay. So in this example, we can run this iMineralysis software, and if you see, we can actually open as many iMineralysis screens you want, as long as your computer can handle it. So I have another iMineralysis screen open with an example for, I think it's 96 wells. So in the setup analysis, we have, this is a different area. So we have, again, our matrix of limits. As I mentioned, when we're doing optimization, that middle point, or what we call the matrix, the value of the coefficient, is not important. It's used only once during the optimization. If you want to include it, you can include it, but in reality, what is important are the limits. Click apply. And what we'll do is that we're going to select just few wells for this example in order to save some time. And also, I'm not going to run it for all the wells because all the intervals. I'm just going to run for interval A and interval B. You can actually have different limits for each of your different intervals. The limits tells you the combination of logs and minerals. In this case, you can have the same limits, but you can have, since you're running them separately, it will get you to different solutions for each of the intervals. So we're going to optimize the coefficients. I'm going to change this to 40 and 5 just to, since we have more wells and more space, we want this to run quickly. And we have another option that is that we can optimize each well, all the wells together, or we can optimize them each well individually. And that is what you will need to do in case you want to look at variations of the endpoints of these coefficients regionally. So I'm going to run it in the two ways. I'm going to run it first combining all the wells, and then I'm going to do it again as individual for each individual wells. I'm going to click prepare. In the prepare window, as you see now, is slightly different than the one that we saw in the previous example. In this case, you have now what we call the diagnostic for the two different intervals. And it's important that you pay attention to this. It's going to look very different when we do this for each individual well. We click start, and we can see that we start running, and this is for interval B. You can see it here on the top. And if you change for interval A, you can see the optimization also running for interval A. Interval A is much more thicker, so it takes longer for each generation to run because it's solving the multimedia analysis again for the entire column. You can have also the tested coefficients. You can see for each of the models, this is the B that already finished, and this is for A that is now doing the optimization. And it takes you again to the results panel. You have a very good match of the logs. and you can change between wells. You can just scroll down with your arrow in your, and you can look at them. Actually, here we just have to click here to see the entire well. But also in the coefficients now, instead of having one matrix of your final coefficients, you have the two of them. So you have the when was the last optimized solution of your coefficients for interval A and for interval B. Okay, so we started with the same ones. You can see here the starting point was the same for both intervals, but it achieved to a different place for the combined solution. Now, we're going to rerun this using the option for each well individually. And we're going to call it individual. So we click on prepare. And when we do that, now this prepare window looks very different because for each of the intervals, you now have a diagnostic for each of your wells. So you have for the well 1712, then for 1723, and so forth. So you have that for interval A and interval B. If you have 90 wells, it will have that for the 90 wells. So we click start. And as we did before, we see we can see the metrics or the optimization for each of the intervals, but now it's not only the interval, it's also the well. So it's optimizing geometrical coefficients in each of your wells, in each of your intervals. In the B here, you can see it has not started yet because it depends on the capacity of your computer. It will jump then directly to the results. And now, as I showed before we had two matrices of solutions. Now we have one for each of your wells, for each of your intervals. So you had 4 wells, 2 intervals. It means that we have 8 solutions. And for the logs, it looks similar. We can actually compare now the solution of the combined optimization versus the other one. You can see they're very similar. If we zoom in, it's kind of hard to see them because they are very close. We were optimizing only 4 wells. But if you look, it's kind of hard to see, but if you look in detail, typically when you do the optimization individually, you get a better solution. If you see the blue is closer to the red than the green, even though both solutions are pretty good, it's typically that of course, when you optimize each well individually, is a better solution. Also, since we have only 4 wells, the difference between the 2 solutions are very close. But when you are solving for 90 wells at a time, the combined solution starts really being not good. So the last thing I want to show you for the software is how can we export. So we export the logs. We can just highlight what we want here, and you include the highlighted wells. You can highlight different wells and include them. We can select which logs to export. It has a default name, but you can change the suffix for anything here, or you can add the prefix, and it will add that to your to your logs. You can export by which solution you want. If you want the combined or the individual, and you have your solution there. You can also export the coefficients too, and this is a very unique feature of iMineralysis. You can export the combined minerals that we selected for each interval A and B. So basically, you are exporting only 2 different matrices, but you can also export in a CSV file, for example, the values for interval A of all your coefficients. You can actually select here in this to the right what information you want in the CSV file. If you want it also allows you to export the average fractions. So like the fraction of the minerals, like the volume of calcite and dolomite, etc., which is usually hard to export in a petrophysical software. You typically need the combination with a geologic software to be able to calculate this kind of averaging. But it also allows you to calculate the errors, and you have the porosity, saturation, and and the coefficients, which is really important too. So you can export the gamma ray of the kerogen, or you can export the density of the kerogen. This is actually the feature we use to be able to map the kerogen density in an area. And it allows you to also order differently in your file. So when you export that way, you export the coefficients. This is the kind of map you can do. So you are doing the optimization each well individually, and then you can plot the kerogen density for each of the wells.